Welcome to The Explainer. Today, you and I are going to step into the shoes of an environmental detective. We're going to explore this absolutely fascinating, completely invisible world of inorganic substances flowing all around us, and yeah, right out of our tops. We'll be learning exactly how scientists identify and measure the hidden chemical culprits lurking in our drinking water. It's a journey from the initial crime scene all the way into a high-tech forensic lab. Okay, so here is our detective's toolkit for today. We'll start with salts in the environment, then move to detecting ions using qualitative techniques, followed by measuring mass and titrations. After that, we'll look at colorimetry and spectroscopy, and finally wrap up with atomic absorption spectroscopy. Let's dive right in. Section 1, salts in the environment. So where do they actually come from? Well, to really understand our crime scene, we have to know how these invisible compounds enter the environment in the first place. You see, water is basically the ultimate solvent. As the water cycle constantly moves water between land, oceans, streams, and the sky, it naturally percolates through soils and rocks, picking up and dissolving minerals along the way. But human activities, they dramatically concentrate these salts and heavy metals in our water supply. For example, heavy rainfall causes agricultural runoff, literally sweeping fertilizers like ammonium nitrate right into our streams. At home, our domestic discharge adds phosphates from everyday washing detergents. And on a massive industrial scale, mining operations discharge huge volumes of wastewater, while fossil fuel combustion from our cars and cities releases highly toxic heavy metals that eventually just leach into the water we all rely on. To ground this science in your everyday life, let's talk about something you've probably experienced: hard water. If you've ever found it super difficult to get a good lather or froth going with your soap, you're dealing with hard water. This hardness is caused by the presence of mineral ions, specifically calcium and magnesium cations. And not only do these invisible ions totally mess with the washing action of your soap, but when you heat them up, they can cause that stubborn, crusty mineral scale to form on the insides of your water pipes and your kitchen kettles. All right, Section 2, detecting ions using qualitative techniques. So, how do we actually figure out who the chemical culprit is? We start with the absolute simplest tool in our kit, the flame test. By just introducing a sample of our unknown water into a hot flame, the heat excites the atoms. When they relax, they emit light, instantly revealing the identity of a metal cation based on a totally unique color. Every metal has its own distinct signature. If your flame turns a brilliant scarlet, you found strontium. A vibrant green, that's copper. Yellow-green points to barium, while sodium gives off this bright yellow glow. It is just a wonderfully simple, highly visual way to unmask our chemical suspects. But, what if we need to be a bit more systematic? That's where scientists use a logical flowchart of precipitation reactions to hunt down unknown cations. It's essentially a process of elimination. We might start by adding a chemical like dilute hydrochloric acid. If a white solid, a precipitate, forms, we instantly know we've narrowed our suspects down to silver or lead. If nothing happens, we just move down the chart, adding ammonia to trigger different, uniquely colored precipitates, like a pale green solid for iron or a deep blue solution for copper. It's a really brilliant step-by-step trap. And guess what? That exact same logical process applies to negative ions, which we call anions. Using a similar flowchart, we might introduce a reagent like silver nitrate. If a precipitate forms, we've caught a specific subset of suspects, maybe chloride, bromide, or iodide. By sequentially adding dilute nitric acid right after that, we can observe whether that solid precipitate dissolves or remains stubborn, which confirms the exact identity of our negative ion. With these charts, we've successfully answered our first question: who is in the water? Okay, moving to Section 3, measuring mass and titration techniques. So we know who the culprit is. Now we have to transition from qualitative to quantitative analysis to find out exactly how much of it is in there. Welcome to gravimetric analysis. This is a procedure where we quite literally weigh the solid evidence to calculate the exact amount of impurities. First, we prepare our sample. Second, we deliberately add an excess of a reacting solution to force every single trace of our culprit to crash out of the water as a solid precipitate. Third, we capture that solid using filtration and wash it carefully to remove any straggling soluble stuff. Finally, we dry it completely and weigh it. By knowing the mass of that solid salt, we can calculate precisely how much of that ion was hiding in our original water sample. But let's be honest, all that filtering and drying, it can be incredibly time-consuming. So often, we use titrations instead. We basically have two different methods to figure out exactly when a reaction is complete, a magical moment we call the equivalence point. A precipitation titration relies on a chemical indicator to cause a sudden, highly visible color change right at that finish line. A conductometric titration, on the other hand, doesn't rely on human eyes at all. It relies on a meter to detect a sudden shift in electrical conductivity the exact moment the reaction finishes. Think about a regular precipitation titration in progress. You're dropping silver ions into a flask until suddenly, boom, the indicator reacts with the excess silver to turn the whole flask a deep reddish brown. That visual cue tells you to stop. But a conductometric setup is completely different. Instead of waiting for a color change, you have electrodes sitting right in the beaker. As ions react and precipitate out as a solid, like barium sulfate, the electrical conductivity of the water naturally drops. The exact second it spikes back up, you know for sure you've crossed the equivalence point. It's precise, it's electrical, and it completely removes the guesswork of watching a flask change color. Section 4. Colorimetry and UV visible spectroscopy. Now we're measuring light. When electromagnetic radiation, like visible light, interacts with atoms, some of that light gets absorbed. But here is a totally fascinating trick of chemistry. The color a solution absorbs is actually the exact opposite of the color our human eyes observe. To remember this, scientists use a quick memory trick. Write out the colors by decreasing wavelength: red, orange, yellow, green, blue, violet. Then write them again right underneath, but starting with green. Green, blue, violet, red, orange, yellow. If a toxic heavy metal solution absorbs violet light, this trick tells you that it will appear green-yellow to your eyes. We are seeing the complementary, transmitted light. Pretty cool, right? We can actually measure this absorption super precisely using an instrument called a colorimeter. We start with a basic light source. The light passes through a specific colored filter, which is chosen because it's the exact complementary color that our sample loves to absorb. That filtered light shoots straight through a glass tube containing our sample solution, and finally hits a detector on the other side. The darker or more concentrated the solution is, the more light it absorbs, and the less light reaches the detector. It's a simple rule. Concentration is directly proportional to absorbance. To actually get a hard number for our environmental investigation, we create what's called a calibration curve. Think of this as creating a custom ruler. We prepare a set of standard solutions where we already know the exact concentration, say 1, 2, 3, and 4 parts per million. We measure how much light each one absorbs and plot those dots on a graph to draw a straight line. Once we have our ruler, we just pop our mysterious unknown water sample into the colorimeter, get its absorbance reading, and track that across to our line to reveal its exact concentration. Now, what's really interesting is how we can upgrade that basic colorimeter into a UV visible spectroscope. Instead of relying on a standard piece of colored glass as a filter, this advanced instrument uses a monochromator, which acts like a highly advanced prism. This allows us to scan across multiple wavelengths and select one exact, hyper-specific wavelength of light that our target chemical absorbs most strongly. It gives our detectives incredible precision, ensuring we aren't accidentally measuring other harmless compounds mixed into the water. And finally, Section 5, Atomic Absorption Spectroscopy. This is the ultimate tool. This brings us to the absolute pinnacle of our detective toolkit. To understand how it works, let's briefly look at atomic emission spectroscopy. Remember that simple flame test from earlier? When atoms get hot, their electrons jump up to higher energy levels. As they fall back down to a stable state, they emit light. If we pass that light through a prism, it separates into distinct, sharp, colored lines called an emission spectrum. Every single element in the universe has a completely unique pattern of lines. It's a literal atomic fingerprint. Then, back in the 1950s, an Australian scientist named Alan Walsh had this brilliant reversal of the idea. He realized that if an atom emits a specific fingerprint of light, it will also perfectly absorb that exact same fingerprint of light. In atomic absorption spectroscopy, or AAS, we use a special lamp made out of the exact metal we are hunting, let's say lead. The lamp shoots the perfect wavelength of lead light through a flame where our water sample is being sprayed. If there is lead in the water, it will absorb the light. By measuring exactly how much of that specific light gets blocked, we know exactly how much lead is present. And this isn't just some lab trick. AIS is an absolute powerhouse. It is capable of detecting 68 different metallic elements. It's the gold standard used in labs worldwide for analyzing real-world samples. Whether it's finding dangerous lead levels in human blood, detecting mercury in the fish we eat, or finding toxic runoff in our drinking water, AIS can spot the culprit. The real-world stakes here are just immense, and this machine is more than up to the task.
AAS is incredibly sensitive. It can reliably detect toxic heavy metals at concentrations of less than 1 milligram per liter, which is less than 1 single part per million. To put that into perspective for you, that is literally like finding a single drop of poison diluted into a massive 50-liter barrel of water. It's staggering accuracy.
So we've journeyed all the way from recognizing hard water scaling up your kettle to using lasers and monochromators to hunt down heavy metals to the part per million. You now know exactly how scientists bring the invisible chemical world into the light. Armed with this ultimate environmental detective toolkit, I have to ask you, what invisible mysteries do you think are flowing from your tap right now? Thank you so much for exploring this with me, and stay curious.